Hey there, I know I said in the overview video that the next one would cover what happens with impairments of the language system, but actually today we're going to look at, as you can see from the title, we're going to look at the semantic system. And you might be wondering, why is there a whole video about one single component in the model? It's just that circle in the middle, right? But that's why we need to do a whole video, because that one component actually covers a whole lot of things and there's a lot of assumed knowledge. So this video will cover what is in it, what happens, what makes up the semantic system, how it works, and how it ties into the rest of the brain. And you may not need to memorize this information per se in the same way that you need to sort of memorize how the model works, but it's still really important, and particularly important when you start seeing people with aphasia. So in that overview video, we sort of pointed out that all of the meaning and knowledge is stored here, and talked a little bit about conceptual features. As we pointed out, when we want to say something, all of the knowledge that we have is somehow converted into words. And equally, when someone says something, we read something, that lights up all of our knowledge about the world, or memory about the world. So how does that one little circle interface with the rest of the brain to do that? First up, what do we mean when we say semantics? So semantic memory, semantic knowledge, and conceptual knowledge are pretty interchangeable. And a good definition I've come across is that semantic memory is the general knowledge of objects, word meanings, facts, and people without connection to any particular time or place. So an example of semantic memory would be a nail gun, or I believe in North America it's called a nailer. But you know what a nail gun is, you know what it does, you know where to find them, maybe what they sound like, what they feel like, the approximate size, etc. All of that's your semantic memory. What would not be semantic memory is remembering the time, your cousin put a nail through his hand playing with a nail gun, or something like that. Because that memory is specific to you and it's specific to a time and place, whereas the general concept of a nail gun or a nailer is your semantic memory, and it's shared by the population. So we'll put that there. Semantic memory, also called semantic knowledge, conceptual knowledge. The next important thing to note is that semantic memory is multimodal. It's not just verbal. So we learn a lot about the world through the modalities other than language. So of course there is a heap of visual semantic knowledge, and there's a whole network dedicated to olfactory or sense of smell semantic knowledge. And there is a network of action, and by action I sort of mean movement and what does it mean to brush? There's a movement knowledge to that concept, and not just the word, the concept itself. There's plenty of information in the auditory semantic memory about what things sound like or what sounds are. There is tactile semantic knowledge, and then of course there is verbal or lexical, language-based semantic knowledge. Now this is not the list, these are just some examples of kind of major semantic modalities. And it's just a really important point for speech pathologists who are always hyper-focused on language, is that there's so much more than language. In fact, there's so many things that we have conceptual knowledge of that we don't have language for. Let's create an example of that. What is this thing? Probably most of you have not seen it. It was kind of the weirdest looking item I could find. Now, you don't know what to call this. You could describe it, you could make up some names, but you don't actually know what its name is. And yet you now have visual knowledge of it. If I gave it to you and you held it, you would have some tactile knowledge of it, and you could remember it, and yet you don't have a specific verbal entry for it. Even if I was to show you what it does, kind of cool, but kind of over the top. Now you know the function of it, and yet you still don't know the name. Now it's called an Alessi juicer. Now you have an entry for it, a Alessi juicer. Now you could have described it once you saw the function, but you didn't have a lexical entry. So my point there is that we have so much more knowledge and memory about the world than just the things we have words for. But although I've described these different modalities, they are all linked. They're highly, highly interconnected. And we can represent that with a diagram, something like this. So if we imagine that each color is its own kind of network, and yet there are interconnections between those networks, and together it makes up the network of semantic knowledge. That goes some way towards describing how this works in the brain. So again, I've just made this model up for illustration. It's not a formal image that you'll see anywhere else. Now, a single concept or entry is typically comprised of representations across multiple modalities. So if we take the example of pancake, the concept of a pancake is made up of obviously the word, and there is tactile information both for sort of hands and tongue, and there's visual information, and there's olfactory and I guess taste information, and all of that together makes up the concept of a pancake. And many concepts favor one modality over others. So obviously if you say the concept of thunder is going to have a very strong auditory representation and some lexical, but not so much others. So this gives you some idea about the multimodality nature of semantic knowledge. But one leading theory is the idea that there is actually, in the midst of this, an amodal or transmodal semantic hub that interfaces between all these modalities. And it would integrate all of these modalities into amodal concepts, amodal meaning no particular modality, just the concept itself. So for example, as we said, pancake might actually have its own entry in here without a particular modality, but it links to those modalities. This is an important point that we're going to add to our summary. Semantic memory is multimodal, not just verbal. But what we're going to do next is be a little bit more specific again. We're going to separate the verbal semantics, which we're going to call lexical semantics from now on, into its own layer. And then the rest of it, we're going to just summarize as conceptual semantics. So I hope this isn't too confusing. Basically, we're saying we've got word-based semantics and everything else. Right, so you can see that within the semantic circle in the PALPA model, there is a lot happening. So much so that it doesn't really fit. So we're going to make the PALPA model 3D temporarily. So semantics is on its own layer, but there's actually two things going on there. There's the lexical semantics and the conceptual semantics, which interface. And now we're really going to dive into that and look at the layers. On this bottom layer, which represents a fair bit of the brain, we have non-linguistic knowledge and sort of pre-linguistic concepts about the world. On the middle layer, the lexical semantic layer, we have the meaning of every word you know. So this layer does not contain the phonemes and it doesn't contain letters, but all of the other meaning-based features of words. And then in the top layer, which is sort of the rest of the PALPA model or the psycholinguistic model, that's where phonemes and letters and all of that other processing happens. So I've given this example before, but when you sometimes know that a word exists and you know what it means, but you just can't think of what it is, that's an example of where the conceptual and lexical semantics have lit up, but they're not traveling to retrieve the phonemes. So we have lexical semantics that does not include the phonemes and the graphemes, and then everything else we will call the conceptual semantics. So we're going to go through some examples now to make this process clear, because this is really important. All right, when you look at a picture like this and you say what it is, mango, there's quite a bit happening there, even though it happens in the blink of an eye. Conceptually, you understand that you're looking at a fruit. And when you understand you're looking at a fruit, all of the connections to fruit are somewhat activated. You also know that it's something sort of tropical, for example. And all of the tropical entries in the lexical layer are also slightly activated. And you can see by looking at that it's quite juicy. And so all of those concepts are also activated. And you can see that each time we do this, certain entries are getting more activation than others. Clearly it's yellow, and so all of those aspects are activated. And then there is even, for example, some size and shape knowledge that is activated. And that activates certain lexical entries. So importantly here, you can see that there are actually two candidates for that picture that are pretty closely activated, and there's not much between them. Perhaps that flavor is something that activates mango and makes that the best candidate for naming that picture. And that representation that matches all of the features that your conceptual system knows that it's looking at is then selected for production, and it travels up to the phonemic system, the output lexicon, the output buffer. It's programmed and then produced. You can see that this is not just a storage system with words and meanings neatly packed into boxes. It's an infinitely complex network with all of these conceptual features linked to different verbal entries. Let's look at an example the other way for comprehension. So someone says the word cucumber. The phonemes are recognized. The phonological input lexicon recognizes that that is a known word and it activates it in this lexical semantic layer. When that word is activated, it has strong connections to all of its features. It's a vegetable, it's green, it's watery, has a long shape, it's crunchy, for example. And then we understand what that word means. Now, this whole system is the basis of understanding not just different words, but very similar words. If two words have a really similar meaning, how can we tell them apart? Well, if we think about these words, king, tsar, and queen, they are all royalty. They are all rulers of countries. And two of them are male, but the queen is tagged to the concept of being female. And even though there's many features that they share, it is that feature that distinguishes them and helps us express ourselves more clearly or understand key differences in conversation. And additionally, tagging something with a location like Russia makes us understand how a tsar differed from a king. Perhaps a less concrete example would be the words growl and snarl. They are both vocalizations, they're both threatening sort of noises, but a snarl, there's something visual about it as well, and a slight auditory change, but you will see bared teeth. So we're going to come back to this word retrieval and selection in a bit, but important to understand that those different layers of concepts versus lexical entries are nonetheless deeply interconnected. So let's talk briefly about how the semantic system is organized, how it's stored, and what are the connections. They are organized by meaning and not by phonemes. So the word rock, in terms of music, has lots of connections which are based on meaning. And those connections in the lexical layer might be key features. Rock typically contains, a guitar and 4/4 rhythm. And it's closely connected to music because it's a superordinate, or music is a superordinate category of rock. It's a category that contains it. There are also subordinate categories that are closely linked. So rock and roll is a type of rock, metal is a type of rock. There might also be links to sort of similar or sibling entries. So all of these meaning-based connections are stronger than anything to do with sound. Two words that sound exactly the same will be stored separately, completely separately in the semantic system. So rock, the music, and rock, the geological thing, they're stored completely separately. And this is why a task such as category naming, can you name as many animals as you can, is so much easier than phonemic naming, because for category naming, there are already these connections between similar things. So to jump from tiger to lion to bear is, a very short distance. Whereas if you're asked to name things starting with T, you have to constantly dip into the phonological output lexicon to check what the names are, but you don't necessarily have strong connections between two words that start with T. Now, this strength and distance of these connections are based on meaning, and we can sort of model this with reasonable accuracy by looking at AI projections of word meaning. Artificial intelligence can do word embedding, which is where they start to understand the meanings of words based on how often they're co-located. And we can sort of view them in a way that somewhat resembles human organization. I'm not saying that it's the same, or that AI, represents the brain, but there's some similarities that we can learn from. Now you can see this is just one projection of these understandings using tensorflow.org, and you can see there are clusters of meaning. So for example, up here, what have we got? It seems to have clustered all these names together. And over here, these are US states. We've got political kind of cluster here. This seems to be a religious cluster. So the AI has understood that these words often occur together and have a similar meaning, and so it has arranged them into these clusters. Now this gives you some idea of how closely related concepts are bundled in the brain, but what's missing here is the connections. So if you could also imagine that each one of these dots has a couple of thousand connections, then it would start to feel a little bit more like the brain. So it could be that one of the names in this cluster, Joe, is really strongly linked to the political cluster, wherever that was. So it's not just about the distance, but it's about the strength of the connection. So remember that there were multiple possibilities activated in that mango example, and that's because it's a network, there's this spreading activation across relevant words. It's not just pulling out a single meaning of a single word, there's this network that lights up. Now this is actually really useful, this spreading activation, because if you think of a word and the nearby neighbours are also lit up, there's a good chance that you're actually going to use one of those words as well as the original target word. And that's a sort of priming effect that helps us be very efficient with our language retrieval. One of the downsides of that is we only need a subset of related terms at any one time. A few real life examples of this, maybe you're doing a crossword and the clue is baddie and you think, oh, it's villain, and that's kind of the most obvious target. But that doesn't fit, it's something else. And it starts with R. Then you have to kind of suppress that really obvious one and go and search what else is related. What are these other connections? What else lights up when I think of baddie? Maybe you want to retrieve an infrequent representation. You want to try to improve your vocabulary for a description, or you're writing a review. So you don't want to say that film was sad. You think upsetting. Okay, what else? Tragic, heartbreaking, compelling, agonizing. Or sometimes you have to switch between possible meanings. So you hear or read a word and you think, okay, no, it's not the most obvious definition. There is a less frequently used meaning of that word. Look that up. That's what it means. So that suppression of the obvious meaning. Those interconnections are really important. Highly interconnected by meaning, etc. Okay. I think you can see just how complex the semantic system is and how important it is to understand some of that. And so that when someone says yacht and we recognize the letters and recognize that we do know that word and it just retrieves the meaning, actually that's retrieving a lexical entry which is lighting up all the conceptual features in more than one modality, etc. This is covered pretty well in Words Fail Me by Lindsay Nichols. There's also some more advanced information in this book, chapters 7 and then 10 to 12. Thank you to Lindsay Nichols for checking over this video and making sure as I tried to explain things I didn't oversimplify or make errors. All right, let's see what you've understood so far with some test questions. What type of knowledge is considered semantic and what is not considered semantic knowledge? General shared knowledge of objects, word meanings, facts, and people, that is semantic knowledge. And knowledge specific to time, place, and individuals is considered more episodic. Next one, what is semantic knowledge comprised of? Choose all that apply. A. Lexical concepts with associated phonemes and graphemes. B. Lexical concepts. C. Concepts across multiple modalities, possibly with a central hub to integrate them. And or D, multiple episodic memories. Let's review each one. A, lexical concepts with associated phonemes and graphemes is not correct because semantic knowledge does not include the phonemes and graphemes, so not A. B, lexical concepts. Yes, semantic knowledge does contain lexical concepts, being the matching of a word concept to its meaning. C, concepts across multiple modalities, possibly with a central hub to integrate them. Yes, this is a more complete description of semantic knowledge. It's concepts across multiple modalities, including lexical concepts, but not only. And D, multiple episodic memories, is a red herring. Which statement is true? A, when you name an object, only the most relevant word receives activation. Or B, when you name an object, multiple related words are partially activated. The answer is B, multiple related words are partially activated under the spreading activation theory. If only it was as easy as A, where you just get the relevant word. It does feel like that to an unimpaired system a lot of the time, but it is in fact B. True or false? Homophones are closely connected in the lexical semantic layer.
Where?
This is false. Concepts are stored and connected by meaning. So even though these two words phonemically are the same, they are not connected within that layer because they have completely different meanings, just like our rock and rock examples. In the semantic network, words may be closely connected for several reasons. Which of the following are reasons? One word is the superordinate category for another word. They are derived from the same root or origin in language history. They share common features in terms of their sensory or conceptual associations. They sound similar even if their meanings are different. The first option, one word is the superordinate category for another word, is true because categories are semantically related. So pet and dog is a type of pet. They are closely connected. The second option, they arrived from the same root or origin in language history, is not one of the reasons, although it may coincidentally be true. The third option, they share common features in terms of their sensory or conceptual associations, is definitely true. It's really the main reason. And the last one, they sound similar even if their meanings are different. I'm sure you understand by now that the way a word sounds is not a reason for it to be connected semantically. Okay, a lot there. It's not as linear and neat as perhaps the rest of the model, but that's really the nature of the semantic system. Next up, I will talk about what sort of errors you see and how that relates to the psycholinguistic models. Thanks so much. See you next time.
Same word, different thing. Wearing. Where have you been? I'm wearing a jumper. Where have you been? Where?
Brilliant.